When we compare lunar gravity and Earth gravity, we are really comparing two vastly different environments shaped by mass, size, density, and distance from their centers. Gravity is the force that pulls objects toward the center of a celestial body, and it is determined primarily by the body's mass and radius. Earth is much more massive than the Moon, and this difference in mass is the key reason why gravity on Earth is significantly stronger. On Earth, the acceleration due to gravity is approximately 9.8 meters per second squared, meaning that every second an object in free fall increases its downward speed by 9.8 meters per second. On the Moon, however, gravity is only about 1.62 meters per second squared, which is roughly 1/6 of Earth's gravity. This means that if you weigh 60 kilograms on Earth, your mass remains 60 kilograms on the Moon because mass does not change, but your weight, which depends on gravity, would be only about 1/6 as much. In practical terms, a person who weighs 600 newtons on Earth would weigh only about 100 newtons on the Moon. This dramatic difference affects everything from how humans move to how objects fall and how structures are built. One of the most noticeable effects of reduced lunar gravity is the way people would walk and jump. During the Apollo missions, astronauts demonstrated that movement on the Moon looks slow and bouncing compared to walking on Earth. Because gravity pulls them downward with less force, astronauts were able to jump much higher and stay in the air much longer. A jump that might lift you half a meter off the ground on Earth could lift you several meters on the Moon with the same effort. The reduced gravitational pull also means that objects fall more slowly. If you were to drop a hammer from a certain height on Earth and drop the same hammer from the same height on the Moon, ignoring air resistance, the hammer would take longer to hit the lunar surface because the acceleration due to gravity is smaller. Interestingly, in the absence of air resistance, all objects fall at the same rate regardless of mass, both on Earth and on the Moon. But because the Moon has virtually no atmosphere, the effect of air resistance is negligible there. This was famously demonstrated when an astronaut dropped a feather and a hammer simultaneously on the Moon, and they hit the ground at the same time, something that would not happen in Earth's thick atmosphere, where air resistance slows the feather significantly. The difference in gravity also has profound effects on the Moon's ability to hold an atmosphere. Earth's stronger gravity allows it to retain a thick atmosphere composed mainly of nitrogen and oxygen, which supports life and regulates temperature. The Moon's weaker gravity cannot hold onto light gas molecules for long periods, especially over billions of years, so it has only an extremely thin exosphere rather than a true atmosphere. Without a substantial atmosphere, the Moon experiences extreme temperature variations, from very high temperatures in direct sunlight to extremely low temperatures in darkness. Gravity also influences escape velocity, which is the speed an object must reach to break free from a celestial body's gravitational pull without further propulsion. On Earth, the escape velocity is about 11.2 kilometers per second, while on the Moon, it is only about 2.38 kilometers per second. This lower escape velocity made it easier for lunar mission spacecraft to lift off from the Moon's surface and return to orbit compared to launching from Earth. The structural implications of different gravity levels are also significant. Buildings and natural formations on Earth must withstand stronger gravitational forces, which means materials experience greater stress under their own weight. On the Moon, structures could theoretically be taller and lighter because they would not need to support as much weight. However, engineers would still need to consider other factors, such as radiation exposure, micrometeorite impacts, and temperature extremes. Human physiology is another critical area affected by gravity. The human body evolved under Earth's gravitational conditions, and long-term exposure to lower gravity, such as on the Moon, can lead to muscle atrophy and bone density loss. In microgravity environments like those experienced by astronauts orbiting Earth, these effects are even more pronounced, but even the Moon's partial gravity may not be sufficient to fully maintain muscle and bone health over extended periods. Scientists are still studying how 1/6 gravity would affect the human body over months or years, especially in the context of potential lunar bases. The difference in gravity also shapes the landscapes of Earth and the Moon. On Earth, flowing water, weather, and tectonic activity constantly reshape the surface, and gravity drives processes such as erosion, landslides, and sediment transport. The Moon lacks liquid water on its surface and has minimal geological activity today, so its landscape is dominated by impact craters that remain largely unchanged for millions or even billions of years. Because gravity is weaker on the Moon, impact ejecta from meteor strikes can travel farther before falling back to the surface, contributing to the widespread blanket of fine dust known as regolith. Even the tides on Earth are connected to gravitational differences. The Moon's gravity exerts a pull on Earth's oceans, creating tidal bulges that result in high and low tides as Earth rotates. While Earth's gravity dominates locally, the gravitational interaction between Earth and the Moon is a dynamic system that influences both bodies. In summary, lunar gravity and Earth gravity differ dramatically due to differences in mass and size, leading to wide-ranging consequences for motion, atmosphere, escape velocity, human health, engineering, and planetary geology. Earth's stronger gravity shapes a world with a stable atmosphere, active geology, and conditions suitable for life as we know it, while the Moon's weaker gravity creates an environment that is stark, airless, and profoundly different in how objects move and how the surface evolves. Understanding these differences is essential not only for scientific knowledge, but also for the future of space exploration and the possibility of sustained human presence beyond Earth. Another important way to understand the difference between lunar gravity and Earth gravity is to look at how gravity is calculated in the first place. According to Newton's law of universal gravitation, every object with mass attracts every other object with a force that depends on their masses and the distance between them. The gravitational force increases with greater mass and decreases with greater distance. Earth's mass is about 5.97 times 10 to the power of 24 kilograms, while the Moon's mass is only about 7.35 times 10 to the power of 22 kilograms. This means Earth is more than 80 times as massive as the Moon. Although the Moon's radius is smaller, which slightly increases surface gravity compared to if it were spread out more, the difference in mass is so large that the resulting surface gravity remains far weaker. The formula for surface gravity shows that gravity depends on mass divided by the square of the radius, which explains why even small changes in radius can matter, but mass is usually the dominant factor. When comparing Earth and the Moon, the combined effect leads to the Moon having roughly 16.5% of Earth's surface gravity. This numerical difference may seem abstract, but it translates into very real physical consequences. Consider projectile motion as an example. On Earth, when you throw a ball at an angle, gravity pulls it downward quickly, limiting how far it can travel before hitting the ground. On the Moon, because gravity is weaker, the same initial speed and angle would send the ball much farther. The arc of the projectile would be longer and flatter, and the time of flight would increase significantly. This principle has practical implications for activities such as transportation, construction, and even sports in a hypothetical lunar colony. A simple game involving throwing or jumping would feel completely different. Athletes would need to relearn coordination because the timing and force required for movements would not match their Earth-trained instincts. Vehicles would also behave differently. Rovers operating on the lunar surface, such as those used during the Apollo missions, were designed with the Moon's gravity in mind. Lower gravity means less traction because the normal force pressing the wheels against the ground is reduced. Engineers had to ensure that the rover's wheels could grip the loose regolith effectively despite the weaker downward force. At the same time, the rover could carry equipment more easily relative to its own structural strength because everything weighed less. This balance between reduced traction and reduced weight is a defining engineering challenge in low-gravity environments. Gravity also affects how dust and particles behave. On Earth, dust settles relatively quickly because of stronger gravitational pull and atmospheric effects. On the Moon, fine regolith particles can be kicked up easily and may travel in long, slow arcs before settling back to the surface. because there is no significant atmosphere to slow them down through drag. Their motion is governed almost entirely by gravity and initial momentum. This posed challenges for astronauts, as the lunar dust was abrasive and could cling to spacesuits and equipment. The way gravity influences fluid behavior is another fascinating difference. On Earth, gravity drives convection currents in the atmosphere and oceans, contributing to weather patterns and ocean circulation. Warm air rises and cool air sinks because of density differences in a gravitational field. On the Moon, without a thick atmosphere and with much weaker gravity, such convection processes are virtually non-existent at the surface. If humans establish habitats on the Moon, artificial environments inside those habitats will need carefully designed air circulation systems to compensate for the altered gravitational effects on airflow and heat transfer. Fire behavior would also differ in reduced gravity. Experiments conducted in microgravity have shown that flames become more spherical and burn differently because hot gases do not rise in the same way as they do on Earth. In 1/6 gravity, fire dynamics would likely be somewhere between Earth conditions and microgravity conditions, requiring special safety considerations for lunar habitats. The psychological perception of gravity is another subtle yet important factor. Humans are accustomed to a constant downward force that defines orientation. On Earth, up and down are intuitive concepts reinforced by gravity strength. On the Moon, while there is still a clear downward direction, the reduced force might alter balance and spatial awareness. Movements that feel natural on Earth could lead to overcorrection or instability in lunar gravity. Astronaut training has shown that adapting to different gravitational conditions requires both physical and mental adjustment. Over time, humans can adapt to new gravitational environments, but the transition period can involve disorientation and coordination challenges. Gravity even influences sound and seismic activity. On Earth, seismic waves travel through a geologically active planet with molten layers and shifting tectonic plates. The Moon, with its weaker gravity and smaller size, has a different internal structure and experiences moonquakes that behave differently from earthquakes. Because the Moon lacks active plate tectonics and has a cooler interior, its seismic activity is less frequent but can last longer due to differences in internal composition and structure. The lower gravity also affects how seismic waves propagate, offering scientists valuable information about the Moon's interior. In addition, the formation history of Earth and the Moon is closely tied to gravity. The prevailing giant impact hypothesis suggests that the Moon formed from debris after a Mars-sized body collided with early Earth. Earth's stronger gravity helped it gather and retain most of the mass, while the remaining debris coalesced under its own gravity to form the Moon. This shared origin explains some similarities in composition, yet the dramatic difference in mass ensured that their gravitational environments would evolve very differently. Altogether, when we look beyond the simple number comparing 9.8 meters per second squared to 1.62 meters per second squared, we see that the contrast between Earth gravity and lunar gravity influences nearly every physical process, from motion and mechanics to geology, atmosphere, engineering, biology, and even human perception. The strength of gravity is not just a statistic. It is a fundamental factor that shapes the character of a world. Human exploration provides some of the clearest real-world evidence of how lunar gravity differs from Earth gravity, particularly during the missions of NASA's Apollo program. When astronauts first stepped onto the lunar surface, they immediately experienced the dramatic contrast between Earth's 9.8 meters per second squared gravitational acceleration and the Moon's much weaker 1.62 meters per second squared. Video footage from these missions shows astronauts moving in a distinctive hopping or loping motion rather than walking normally. This was not merely for style or experimentation. It was an efficient adaptation to reduced gravity. On Earth, walking relies on a controlled forward fall, where gravity pulls the body downward and friction with the ground prevents slipping. On the Moon, with gravity only about 1/6 as strong, the downward pull was weaker, making traditional walking less stable and less efficient. Astronauts found that bounding strides conserved energy and provided better balance in bulky spacesuits. The spacesuits themselves were designed for use in low gravity, but still had mass. Although the astronauts weighed less on the moon, their mass and inertia remained the same. This distinction between mass and weight is critical. Mass measures how much matter an object contains and does not change with location, while weight is the force exerted by gravity on that mass. Because inertia depends on mass, astronauts still had to exert significant effort to start or stop moving, even though they felt lighter. For example, if an astronaut pushed a heavy piece of equipment, it would resist acceleration just as much as on Earth due to its unchanged mass. But once moving, it would weigh less and press less firmly against the surface. This combination of reduced weight and unchanged inertia required careful control to avoid falling or losing balance. The moon's weaker gravity also influences orbital mechanics in a different way compared to Earth. Satellites orbit Earth at various altitudes, held in place by the balance between their forward velocity and Earth's gravitational pull. Around the moon, the same principle applies, but because lunar gravity is weaker, spacecraft can maintain orbit at lower speeds. This reduced gravitational pull was a major factor in mission planning. During the Apollo missions, a command module orbited the moon while a lunar module descended to the surface. The energy required to leave lunar orbit and land was far less than what is required to launch from Earth's surface into orbit. This difference translates into fuel savings and simpler propulsion requirements for takeoff from the moon. If humanity plans to establish a permanent presence on the moon, this lower gravity could make it an ideal staging ground for deeper space exploration, such as missions to Mars or beyond. Launching spacecraft from the moon would require far less energy than launching from Earth, thanks to the lower escape velocity and weaker gravitational binding. Gravity also determines how atmospheres evolve over time. Earth's stronger gravity allows it to hold onto gases like nitrogen, oxygen, and carbon dioxide. These gases move at high speeds due to thermal energy, but most do not reach escape velocity because Earth's gravitational pull is strong enough to keep them bound. On the moon, however, lighter gases can more easily achieve escape velocity and drift into space. Over billions of years, this process left the moon with only a tenuous exosphere, composed of trace amounts of helium, neon, and argon. Without a thick atmosphere, the moon lacks weather systems, wind erosion, and the protective shielding from harmful solar radiation that Earth's atmosphere provides. The absence of an atmosphere combined with low gravity also means that meteor impacts on the moon are more direct and unbuffered. On Earth, many smaller meteoroids burn up in the atmosphere before reaching the surface. The moon has no such protective layer, so impacts are more frequent and leave well-preserved craters. Because gravity is weaker, debris ejected during impacts can travel farther before falling back down, creating extensive ray systems that stretch across the lunar surface. These features remain visible for immense spans of time because there is little erosion to erase them. In contrast, Earth's stronger gravity, combined with water, wind, and tectonic activity, constantly reshapes the surface, gradually erasing most impact craters over geological time. Another important consequence of gravitational difference lies in long-term planetary stability. Earth's gravity helps maintain a stable atmosphere and supports a dynamic interior driven by residual heat and radioactive decay. This internal activity powers plate tectonics, volcanic eruptions, and a magnetic field generated by the motion of molten iron in the core. The moon, being smaller and less massive, cooled more quickly after its formation. Its weaker gravity could not retain as much internal heat, leading to a geologically quieter world today. Although the moon experienced volcanic activity in its early history, forming the dark plains known as Maria, it no longer shows widespread active volcanism. The contrast highlights how gravity influences not only surface conditions, but also internal planetary evolution. Even biological considerations for future lunar settlers revolve around gravity. Scientists are studying whether 1/6 gravity is sufficient to support normal development in plants and animals. Gravity affects how fluids circulate within living organisms, how roots grow in soil, and how cells sense direction. Experiments conducted in orbit, where microgravity dominates, show significant changes in muscle mass, bone density, and even gene expression. The Moon's gravity, being stronger than microgravity but weaker than Earth's, represents an intermediate case. Understanding this environment is essential before establishing long-duration habitats. In summary, the experiences of astronauts, the mechanics of spacecraft, the retention of atmospheres, the shaping of landscapes, and the internal evolution of planetary bodies all reveal the profound consequences of the difference between lunar and Earth gravity. What may begin as a simple numerical comparison unfolds into a comprehensive explanation of why Earth is vibrant and life-sustaining while the Moon remains stark and silent, shaped by a gravitational force that is steady yet far gentler than our own. Beyond exploration and surface activity, the contrast between lunar gravity and Earth gravity plays a crucial role in long-term habitation planning, resource utilization, and the broader future of human civilization in space. As agencies like NASA move forward with programs such as Artemis program, understanding how 1/6 gravity affects infrastructure, health, and sustainability has become a top scientific priority. Earth's gravity has shaped every aspect of human biology over millions of years. Our skeletal system depends on regular mechanical loading to maintain bone density. Our muscles rely on constant resistance to preserve strength. Even our cardiovascular system is tuned to pump blood efficiently in a 9.8 meters per second square environment. On the Moon, where gravity is only 1.62 meters per second squared, the body would experience a dramatically reduced load. Studies conducted aboard the International Space Station show that in microgravity astronauts can lose significant bone mass and muscle strength in just a few months. While lunar gravity is stronger than microgravity, scientists are still uncertain whether it is sufficient to prevent long-term degeneration. Countermeasures such as resistance exercise, specialized suits that simulate loading, and possibly rotating habitats to create artificial gravity may become essential components of lunar living. Gravity also affects how fluids distribute within the human body. In microgravity, fluids shift toward the upper body and head, leading to facial puffiness and increased pressure in the skull. On Earth, gravity pulls fluids downward, maintaining a natural distribution. In lunar gravity, the fluid shift would be less extreme than in orbit, but still different from Earth conditions. Researchers must determine how this altered fluid balance might influence vision, cardiovascular function, and long-term health outcomes. These biological considerations highlight that gravity is not merely a background force, but an active participant in sustaining life as we know it. From an engineering perspective, reduced gravity presents both advantages and challenges. Heavy machinery, habitats, and shielding materials would weigh less, making transport and assembly easier once delivered to the Moon. Construction techniques could take advantage of lighter loads, potentially allowing for larger spans and thinner structural supports compared to Earth-based buildings. However, lower gravity also means that loose materials behave differently. Lunar regolith is fine and powdery, and without strong gravitational compression or atmospheric weathering, it remains loosely packed. Foundations must be carefully designed to prevent settling or shifting. Furthermore, because gravity influences how heat rises and air circulates, habitat ventilation systems must compensate for weaker natural convection. Fire safety design would also differ, as flames in reduced gravity environments burn in altered shapes and may spread unpredictably. Transportation systems on the Moon would operate under unique constraints. Rockets launching from the lunar surface benefit from lower escape velocity, but landing requires careful control because there is no thick atmosphere to provide aerodynamic braking. On Earth, spacecraft returning from orbit rely heavily on atmospheric drag to slow down. On the Moon, descent must be managed almost entirely through propulsion. At the same time, lower gravity reduces the energy needed to move materials into lunar orbit, potentially making the Moon a strategic hub for assembling spacecraft intended for deeper space missions. Mining and resource extraction are additional areas where gravity plays a defining role. Extracting water ice from permanently shadowed craters near the lunar poles is a major objective of current exploration strategies. In lower gravity, excavation equipment may need anchoring systems to prevent lifting off the ground during operation. The reduced downward force affects traction, drilling pressure, and material handling. Engineers must rethink traditional mining techniques to suit the lunar environment. On a planetary scale, gravity also influences long-term orbital evolution. The gravitational interaction between Earth and the Moon causes tidal forces that gradually slow Earth's rotation and push the Moon farther away at a rate of a few centimeters per year. Earth's stronger gravity creates tidal bulges in the oceans, while the Moon's weaker gravity responds to Earth's pull in a more subtle way. Over millions of years, this interaction has stabilized Earth's axial tilt, contributing to a relatively stable climate. In this indirect but profound sense, lunar gravity plays a supportive role in maintaining conditions favorable for life on Earth. Educationally and philosophically, comparing lunar and Earth gravity deepens our understanding of how delicate planetary conditions can be. A slightly smaller Earth might not have retained its atmosphere. A slightly larger Moon might have developed more sustained geological activity. The balance of mass, radius, and gravitational strength shapes planetary destinies. Gravity determines whether a world can hold oceans, sustain weather, and protect life from radiation. It dictates how landscapes form and how living organisms evolve. In the case of Earth and the Moon, two bodies formed from the same cosmic event now exhibit dramatically different realities because of differences in gravitational strength. As humanity stands on the threshold of returning to the Moon and potentially establishing permanent settlements, the contrast between lunar gravity and Earth gravity becomes more than a scientific comparison. It becomes a practical guide for survival and expansion beyond our home planet. Every step taken on the lunar surface, every structure built, and every biological system studied will reinforce the fundamental truth that gravity is one of the most powerful forces shaping the identity of a world. As we arrive at the final stage of this exploration of lunar gravity versus Earth gravity, it becomes clear that gravity is not simply a force measured in numbers, but the defining characteristic that shapes the identity, behavior, and destiny of a planetary body. The difference between Earth's gravitational acceleration of 9.8 meters per second squared and the Moon's 1.62 meters per second squared represents far more than a mathematical ratio. It represents the difference between a living world and a silent one, between oceans and dust plains, between breathable skies and a near vacuum. These two worlds, though closely linked in space and history, demonstrate how gravity governs nearly every physical and biological process. Earth's stronger gravity gives it the power to hold a dense atmosphere, sustain liquid water on its surface, and maintain long-term geological activity. Its gravity keeps oceans bound to the planet, drives river systems downhill, and enables the water cycle that supports ecosystems across continents. The Moon, with only 1/6 of that gravitational strength, cannot hold thick layers of gas or stable surface water under normal conditions. Instead, it preserves a stark record of cosmic history in the form of impact craters that remain largely unchanged for billions of years. Where Earth's gravity contributes to erosion, renewal, and transformation, lunar gravity allows preservation and stillness. The influence of gravity also extends deeply into planetary interiors. Earth's greater mass generates higher internal pressures and temperatures, which in turn drive mantle convection and plate tectonics. These processes recycle crustal material, release gases through volcanism, and help regulate atmospheric composition over geological timescales. The Moon, being smaller and less massive, cooled more rapidly after its formation. Its weaker gravity could not maintain the same level of internal heat and pressure, leading to a geologically quieter present. Although vast basaltic plains formed early in lunar history, active large-scale volcanism has long since diminished. Thus, gravitational strength is directly connected to whether a world remains dynamically active or gradually becomes dormant. In terms of space exploration, the contrast between Earth and the Moon presents both challenge and opportunity. Earth's gravity well is deep, requiring powerful rockets and large quantities of fuel to reach orbit. Launching from Earth demands overcoming not only gravity, but also atmospheric drag. By contrast, launching from a moon requires far less energy due to its lower escape velocity and absence of a thick atmosphere. This distinction positions the Moon as a potentially valuable platform for future deep space missions. If infrastructure is developed on the lunar surface, spacecraft assembled there could depart for destinations such as Mars with significantly reduced fuel requirements compared to launching directly from Earth. In this way, understanding and leveraging lunar gravity could become a cornerstone of humanity's expansion into the solar system. At the same time, reduced gravity introduces long-term biological uncertainties. Human beings evolved entirely within Earth's gravitational field. Our bones remodel themselves in response to weight-bearing stress. Our muscles maintain tone through resistance against gravity. Even our sense of balance relies on gravitational cues interpreted by the inner ear. Prolonged exposure to environments with reduced gravity, such as those experienced by astronauts aboard the International Space Station, has demonstrated the fragility of these systems when gravitational loading decreases. The Moon's partial gravity may mitigate some of these effects compared to microgravity, but it is unlikely to replicate the full protective influence of Earth's stronger pull. Determining whether 1/6 gravity can sustain healthy human development across generations remains an open scientific question. The answer will shape decisions about permanent lunar settlements and the feasibility of long-term habitation. Beyond science and engineering, the comparison between lunar and Earth gravity carries philosophical significance. It reminds us that the conditions supporting life are neither random nor guaranteed. A planet's mass and size determine its gravitational strength, which in turn dictates atmospheric retention, surface conditions, and internal dynamics. Earth's gravity sits within a range that allows for stability without crushing complexity. It is strong enough to anchor oceans and air, yet not so strong as to prevent movement or technological advancement. The Moon illustrates what happens when gravity falls below that threshold for sustaining an Earth-like environment. Despite sharing a common origin, the two bodies evolved along dramatically different paths because of differences in gravitational force. Ultimately, lunar gravity and Earth gravity represent two expressions of the same universal law, operating under different scales of mass and radius. The comparison highlights how a single physical principle can produce worlds of striking contrast. As humanity prepares to return to the Moon and perhaps establish a sustained presence there, the lessons drawn from understanding gravity will guide habitat design, medical research, transportation systems, and resource management. Gravity will determine how we walk, build, grow food, and protect ourselves. It will influence the feasibility of industry and the long-term health of settlers. In closing, the story of lunar gravity versus Earth gravity is a story of balance, adaptation, and possibility. Earth's gravity created the environment in which humanity emerged. The Moon's gravity challenges us to adapt beyond that familiar framework. By studying and respecting these differences, we gain not only scientific insight, but also the practical knowledge needed to extend human presence beyond our home planet. Gravity, though invisible and constant, is the architect of worlds, and in understanding its variations between Earth and the Moon, we better understand both our origins and our future among the stars.